Hey everyone, so today I'm going to implement a max heap from scratch, or I think a min heap, I'm just going to show you how to implement a heap in general. It could be a max heap, it could be a min heap, but I'm going to show you how to implement it from scratch. So don't get scared off if you think that implementing heap is going to be really hard. I'm going to try to do this in under 20 minutes, and yeah, hopefully I can get it within under 20 minutes, and I'll explain everything end to end of how it works and implement the whole thing from scratch in Python. So let's just get straight into it to not waste anyone's time. So, so what is a heap? A heap is actually implemented as a binary tree, and more specifically, it's a complete binary tree. So what does something mean to be a complete binary tree? A binary tree in general is any tree that has one or has 0 to 2 children nodes. So you can see this is a binary tree, right? This is a binary tree. A complete binary tree is a very specific type of binary tree where the tree is filled out from left to right completely except for the last row. So this isn't a complete binary tree because it is filled up from left to right except for the last row. Well, it basically means there's no gaps in it. So if there was a node here, that would turn this into a complete binary tree, right? That would actually be a complete binary tree right there. And let's also, if we delete this node right here, this is also a complete binary tree. This is a complete binary tree. This is a complete binary tree. This is a complete binary tree. Or what? This is a complete binary tree. But this is not a complete binary tree. Essentially, a complete binary tree is where all the levels are filled out fully except for the last row, and the last row is filled out from left to right with no gaps. Yeah, that was a mouthful. That's kind of what a complete binary tree is. So again, this is not a complete binary tree. Um, this is a complete binary tree. And just this is a complete binary tree. If we added this node, that's not a complete binary tree because this is missing. But if we added that, that's a complete binary tree. And the reason why that's important, because it pretty much keeps the levels of the tree as minimal as possible. So that means to get to the bottom, it only takes log n of time, where n is the number of nodes. Because yeah, if you probably studied binary trees a lot, they can digress basically to a linked list if they weren't balanced. So yeah, basically keeping it as a complete binary tree keeps the whole tree balanced, and it doesn't end up something like this, which digresses to a O of n runtime because you're just traversing a bunch of nodes one by one, right? So this is a more efficient way to store it than to the left. What else? So one thing we could actually do is, since we're talking about binary trees, you might be thinking that we can only implement this binary tree using nodes, but you could actually just implement a heap using a straight up list. And it's pretty easy, and I'll show exactly how you do it. And the reason why you can use a list to pretty much build a heap is because it's a complete binary tree. So if you think of this complete binary tree, right? This is if we store this in an array, this is the 0th element, this is the first element, this is the second element, this is the third element, this is the fourth element, this is the fifth element, this is the 6th element, right? So if we stored that in a heap, right, or in a list right here, the 0th element could be this, the first here, the second here. Like, we could essentially store it in a list because we could assign indices from left to right on this complete binary tree. And then pretend we need to delete an element from the heap. We essentially just need to pop from the back of the list. So I'll show exactly how that looks. But yeah, I think just understand what a complete binary tree is, and then you'll understand why it could be used, or why we could use a list there. So heaps pretty much have two operations: a heap push and a heap pop. And heap push pretty much pushes an element onto the heap. So let's do an example actually. I did this on stream already, and I think I give a really good example over stream, or get really good explanation over stream. So let's see. So the heap has these operations, which is heap pushing and heap popping, and then you could peek the top element, and then you could also these are more low key, the increment and decrement, so we won't need to worry about that. But let's work on heap pushing and heap popping, and we'll show how you build. And let's do a min heap. And if you don't know why we even need to use a heap, it's used for priority queues. Priority queues use a heap, and also for questions like this, where we need to get the kth largest element in an array. This is a very popular question. You're gonna need to understand what a heap is. So yeah, let's just go through a list. So basically, let me take a step back. Essentially, what a heap does is it keeps, if we have a max heap, what it does is it keeps the greatest element at the very top of the heap, and then when you pop out like that last element, or that greatest element, the next greatest element is gonna bubble up to the top of the heap, right? So yeah, it essentially, in any question where you want to know, when you want to keep track of the smallest or something like that, or the largest, so like kth largest element, you're gonna start thinking of a heap, right? Because yeah, that's what the data structure does, and I'm sure you probably know what a heap is if you're looking up this video. So let's just get straight into like this heap push portion, and we'll just, if we walk through example, it'll all make a lot of sense for you. So let's just do, let's work on a min heap where the smallest value bubbles up, because that's what we're gonna use here. So let's do 5, 2, 1, 10, 3, 0. So we want the smallest element to bubble up. And let's just work through these these are the key operations: heap push and heap pop. So let's just work from left to right, inserting these into the heap, and see how the tree builds out. I think that will help people see it better. So we start with the 5, we push that on, right? The heap's just starting, and as I mentioned, we're doing a min heap, so the smallest element should bubble up to the top. I'll just write that. Min heap, smallest element at, and we're gonna visualize it like a binary tree first. So let's see, we insert the 5. Now we insert the 2. So how we do it is, how we usually do it is, we're gonna push the element onto the heap by adding it to the next available node and then bubbling it up. So let me just copy and paste this. So heap push. So these are what we're gonna do. We're gonna pretty much add it to the next available node and then bubble it up. So we have the 2. So the next available node here, because we said it's a complete binary tree, since the first row is filled up, the next area to put it is on this next row. So we add 2, right? And then we start bubbling it up by just comparing it to its parent. If I'm smaller than it, then I do the swap. So it's smaller than 2, or 2 is smaller than 5, so we swap. And then we leave it as is. We put 1. Where does 1 go? It's the next available. It goes right here. Right? Now we add it to the next available node, then we bubble it up. Okay, now we have 10. Right? 10, we add it to the next available node, which is right here. And then what? We bubble it up, but it's actually larger than 5, so we already don't want to move it up. Where does 3 go? The next available. What happens here? We compare 3 with its parent and bubble it up. 3 with 1, it's great. It's not smaller than it, so we just leave it. And you could see the heap invariant is pretty much that all nodes under me, or I'm less than all the nodes under me. So 1 is actually smaller than 3 and 2. But even if you look at a node like 3, it's smaller than its children. Finally, let's add 0. We add it to the next available spot, right? It's smaller, we swap. And then it's basically smaller than the 1, so we swap. And you see how the smallest values kind of bubble it up, kind of bubble up to the top. And then after each push, we should be able to know that the top element of the heap is actually a 0, right? Or yeah, like the smallest element in the heap is actually 0. So let's work on heap. Let's start heap popping. So how are we gonna do this heap pop? So we have this heap pop. So we pop the element from the heap. You see why it's a log n operation though? Is because we just put it at the very bottom and then we just bubble it up. So at most it's gonna have log n comparisons and log n flips. So how do you do a heap pop? So first, when we do heap pop, that means we want to pop out the smallest element in the heap, right? So in order to do that, pretty much just swap the first element in the array, or basically the root, with the last one that was popped in or pushed in. So we pop this. And then what we do is we pop, and then we remove this node because that we're gonna return that back to the user. And then now we start bubbling this node down. So what we do is we look at our 2 children, 2 and 1, and we swap nodes with the one that's smaller than it. So we're smaller than 1, so we do that. And then now we have no more nodes to swap with, and now you could see the heap invariant still stays. Sorry, let me move myself. The heap invariant here still stays where the smallest value is at the bottom. Or sorry, the smallest value bubbles up to the top because we have a min-heap. Let's do another one. Let's do pretend. Yeah, pretend 2 was here. Right? Pretend 2 was here. Or pretend it was like this. This is still a valid heap. So 1 is smaller than 2. And this is still a valid heap right here, right? Because pretend we added the 3 or pretend we added the 5, this is still a valid heap because every value is smaller than its 2 children, right? And that is applied recursively. So what do we do when we want to pop this out? We pop 10 here, right? So we want to pop out 1. So we're going to return 1 back to the user because that's the smallest. And then at that point, we start bubbling this down. Is 10 greater or less than 2? No, it's not, so let's switch it. Right? Then we get here. Now is 10 less than 3? It's not, so we switch it. Right? And when we're looking at our children, we want to take the smallest one. So you see here, I didn't swap with 5 is because I want to swap with my lowest. Because pretend I swap with 5, right? Then I need to probably move 5 down after, right? And that would work, but it just leads to way more operations. So usually you just want to swap with the value that's the smallest between your left and the right. So yeah, that's how we do heap pop and heap push. Hopefully I explained it correctly. And then lastly, what we're going to do is peek. We have an operation called peek, which pretty much just returns the top element. So this is no longer a heap now. So let's just get it back into a heap state. So 2 is the smallest, 3 would have bubbled up, and 10, like, it would have went all the way down here. And you can see it's still a complete binary tree. I just got to keep hammering it home what a complete binary tree is. So now what? What do we do? Let's peek. Pretty much the peek operation just lets you look at the top of the heap and lets you know what the value is. So yeah, let's pretty much implement this from scratch. Yeah, heaps. So let's start with a heap. And like I mentioned, we're going to implement this using an array. Then yeah, we're going to implement this using array, and then we're going to have a couple operations: heap push, self. Heap push, where we'll pass in a value that we're going to push onto the heap. Heap pop, and this will return us back a value. And yeah, these are the operations that we pretty much need to care about for now. Let's just go ahead and implement it. So what do we do when we do a heap push? Like I said earlier, when we do a heap push, we add it to the next available node, and then we bubble it up. So since we're using an array, pretend this is the 0th index, this is the 1 index, this is the second index, this is the third index. And if we are looking at this like an array, this would be like, we'd have 2, 3, 2, and 10. So what I mean by pretty much pushing it to the next available node, pretend we want to push the value 6 here into the heap. We pretty much just need to append it to the back of this list, right? And then start bubbling it up if it's lower. So how do we bubble it up? Pretty much, yeah. So let's just implement pushing it onto the back, and then we can work on bubbling it up after. So we have heap push, then we'll say self dot array dot append the value, right? That kind of bubbles it up. And we'll say the current index. So we'll say the current index. We need to store the current index because we need to locate our parent. Current index equals the length of self.array. So if it was the 0th one, that would be the first one to push in. So we'll say while the current index length of self.array, right? So now we pushed. Now pretend we're at 5. We pushed it onto the stack, right? Let's just go from scratch here. So we have our list. We put 5 here, and then this is what it looks like as a heap. So now let's do 2. So 2. We said that we have to do 2. So we said this is the 0th index. This is the 1th index, or the first index. How do we find our parent? Because we need to see if we're going to swap by them. We can do some simple math. Let's just do like, this is the second index. Let's look at it like this. 0, this is the 0th index. This is the 1th index. This is the second index. This is the third index. This is the 4th index, right? So how do I find my parent? I think all we need to do is take our current value, minus 1 it, and divide it by 2. Or just divide it by 2. So what's 1 divided by 2? 1 divided by 2 equals 0. Okay, that gets its parent. What about 2 divided by 2? Well, this equals 1, right? So actually, yeah, what we need to do is take the current index minus by 1 and divide by 2. So take I minus 1 divided by 2. And I'm doing 2 doubles here on purpose because that's an integer division. So what is 1 minus 1 divided by 2 equals 0. 2 minus 1 divided by 2 equals 0 as well. What's 3 minus 1 divided by 2 equals 2 divided by 2? That gives us 1, right? what's 4 minus 1, which is 3, divided by 2? 4 minus 3 divided by 2 equals, 4 minus 1, 3 over 2 equals 1.5, and then you take the floor of that, you get 1. So you could see how that's how we get our parent. So let's just implement that. So basically what we said is while the current index is not equal to 0, that means we're not at the top. And then we'll get our parent. Parent equals index, or current index, like what I said, current index minus 1 divided by 2. Right? That gets us our parent. While the current index is not equal to 0, and self dot array of the parent. So basically, if while the current index is not equal to 0, that means when we look up, or that means we're not at the root, and the self dot parent is greater than the current value, we're going to want to do a swap, right? So what we're going to do the swap, what we can do is we can take self.array of the current index, self.array of the parent, and then just swap them. It's a lot of talking. What am I at? 21 minutes? Okay, this takes actually a while, huh? So yeah, we pretty much swap them, current index, parent, and we take the parent and we swap it by the current index. And then let's take the current index and make it equal to the parent. So now we're looking at, because we swap with the parent, now we're looking at the parent node, and then we want to be able to like calculate its parent. So now we calculate the next parent, and that's kind of how things bubble up. And then let's just like print self.array and then see if everything bubbles up. So in a lot of interviews you're going to actually have to write some test cases. So let's do heap, right? And we'll take our example. Where's our example? This is our nice example. Elements. So for elements, what we're gonna do is we're gonna do heap push the element. Each time we're gonna print the array, and hopefully we should see the smallest element bubble up to the 0th index of the array. So let's just it's 5. When we add 2, that bubbles. When we add 1, that bubbles. We see 1, that bubbles. And finally, so now our heap push is adding. And let's implement a heap, or let's implement a peek operation quick. So peek, if the length of dot array equals 0, raise exception, empty heap. Otherwise, return self.array at the 0th. So that's how we check what's at the top. So when we peek, it should always give us the smallest element in the heap. And now let's work on heap popping, right? This one's a little bit more complicated. So yeah, pretty much we have the heap. What we need to do is let's see how this heap gets built again. What is it? So like I mentioned right here, we could actually just construct this tree by looking at the values here. So this should be the root. This should be the so it's like this is the root 0. 3 goes over here. 1 goes over here. 10 goes over here. Like you can look at it like this. Sorry. 5 goes over here. And then 2 goes over here. Right? this is how the heap is looking, and it's following the the heap invariant is holding. So what do we need to do when we pop? Like I said, we need to swap this one with the smallest value, right? And then pop that out. So let's do that. So let's just say we take this, right? And we take the 0th element and the last element, and then we swap it. We put the 0th element, or we put the last element in the 0th element, and then we put the 0th element in the last element. We do the swap, and then let's do result equals self.array.pop. That gives us the last one. At some point, we're gonna want to return that, but that's the value. That is essentially what this does. We take the 0 and we already popped it. Now we're looking at the 0th index, and we need to bubble it down by taking the lowest child. So let's just say current index equals actually 0, and then we'll say while, basically while true. We'll try to break out of this at some point. So how do we figure out our left index? How do we find our left child and our right child? Well, we can pretty much do math here. So if this is 0th index, is the 1th index, is the 2nd index, how do we find its slot in the array? What we can do is we can take its current index, and since it's we can pretty much take the current index and times it by 2 and add 1. So what's 1 times 2 equals 2? So pretend we're at this value and we want to find its left children. What's 1? So what I said is we do index times 2 plus 1. That gives us the left child, right? How do we get the right child? Index times 2 plus 2. That's how we get our right child, right? Right child. I don't know. I just spelled that terribly. Right. So what's 1 times, or what's the index here? What's 1 times 2 plus 1? 1 times 2 is equal to 2 plus 1 equals to 3. See how that's the left? What's 1 times 2 plus 2? 1 times 2 equals 2 plus 2 equals 4. You can see that it properly gets the right child. So what's 0 times 1? Yeah, or sorry, what's 0 times 2 plus 1? 0 times 2 plus 1 gives us here. What's 0 times 2 plus 2? That gives us here. So you can see that this formula gets us our left and right children. So that's kind of what we have to do here. We have to get our left child. The left index, like I said, is like the current index times 2 plus 1. What's the right index? Equals current index times 2 plus 2, right? Now we need to get the left value. So the left value equals, so since we're looking up, the index, or since we're looking down, the index might go out of bounds. So what we'll do is if the left index is greater than or equal to the length of self.array, we're gonna want to return some value that, since we're trying to minimize, or we're trying to compare something that is smaller, and then only flip if it's smaller. We're do float infinity here, because we never want to swap with, that's our default, because we don't want to swap with something bigger than us. So it kind of ignores that. Else, what do we have here? Else, actually, we go self.array at the left index. Now we're gonna do that with the right. So the right. So if the right index is greater than that, then, or let me put my ice cream in the fridge real quick. 1 second. Just pause out. I thought I could do it quick before my ice cream thawed. But yeah, that's the right val. if the right index is greater than, we just want to do float infinity because we don't want to swap with something out of bounds. Otherwise, we grab it. And then basically what we're going to say is if any of them are smaller than my current value, I'm going to want to swap with them. So if left val is less than the result, or the right val is less than the result, if any of these are smaller, we're going to want to swap. So we're going to perform swap. Otherwise, we're just going to break out this loop because there's nothing to swap, so we already bubbled it down as far as it can go. So we know that the left val, the left val or the right val is less than the result, right? So essentially what we're going to want to do at this point is we're going to want to take the one that's smaller than the other one, because one of these are smaller than the result. So I just want to or both of them could be smaller than the result, but I want to take the one that's smaller, the smallest, and swap them. So what I'm going to do is if the left val is actually less than the right val, I'm going to want to perform the swap, but with so I'm going to take the current index, right? And the left so since the left one is smaller, then I want to swap with it. So I'm going to take the left index, the current index and the left index. I'm going to swap them. I'm going to take the one at the left index and put it on where the current index. And I'm going to take the current index. So that's going to swap them. And now I'm going to take my current index, actually going to be equal to my left index now, right? Else the right value is smaller, so we just do that for the right side. And then yeah, and then that's pretty much what we do. And then that's pretty much bubbling it down. Now let's just print the array. Print.array. We could say result is result, and then we also have like the current array. So yeah, so let's now let's do for I or range elements print, or we're gonna do heap pop. So that should, after we push everything into every element into the heap, when we start popping, it should be popping the smallest element every time. So it should go 0, 1, 2, 3, 5, and 10. So let's just run this. Oops, already out of bounds. Oh wait for. Okay. So it gives you 0, result is 0, then 2, then 1. Oh, you could already see that. Okay, after I pop out the 0, the 1 should have bubbled up there, so I already wasn't doing this right. Let's take a look. So we do the current index. Let's get to the deeper values and just see if it's working. Wait, let's see. So let's after we do the, let's see what's happening here. Why is 2 bubbling? Why is 2 not bubbling up, or 1 not bubbling up? So let's draw this out. So we just popped the 0. And then this is the array, this is the heap that we got. 2, 3, 1, 10, 5, right? Where was 2 before at the start? 2 like this. So initially we had 0, 3, 1. So I'm just debugging this live real quick. 10, 5, 2. So we're gonna flip this. We're gonna return 0. And then we're left with this. We're not bubbling it down properly. So let's do current while true. The current index is 0. If the left index, current index, left index. What's happening here? Are we updating the indexes, Carl? Let's see if it just breaks right away. If the left val is less. Oh no, because we're looking at the result. So what we're gonna do? We need to look at the new top value, which is we're pretty much like if there even is a new top value. So if the length of self.array equals 0, then we just return result, right? Otherwise, we have a new top value which is self.array 0. So we're gonna move down this new top value. So this is the new top value. We're gonna pretty much move it down. Actually, do we even need this? We'll just say, we'll just look at the current index because we're gonna be bubbling it down. So we're just gonna say left val is less than or equal to, where do we hold result? So what we're gonna do is, if the left val is self.array current index, if the left val is smaller than the current index, or dot array current index, something like that. Now let's run this. Okay, cool. 0, 1, 2, 3, and then 5. You can see that it's working as we expected. It's popping them in order. So you see it pop 0 and then it bubbled up 1. Then it popped 1, then 2, the next smallest bubbled up to the top. Then 3, the next one bubbled up to the top. And pretty much, yeah, we already implemented everything. Let's just copy and paste this into our code right here. What's the time? 37 minutes? Okay, this actually takes a while, huh? It's like an interview speed. So let's do small bug there. What am I doing? Self.array. Heap push, heap pop. So so we can solve this using a heap by only keeping the heap at most size 2 and then returning back the top of, like we do a min-heap. Okay, min-heap equals, we take our heap and we create this, right? Then we said for num in nums, what we're gonna do is min-heap dot heap push the num if let's find a length. Length array length dunder method Python. So we just need to implement this length. Yeah, let's do this. Current self dot length of self dot array. So we have our heap. If the length of our min-heap is actually greater than k, then we'll do min-heap dot heap pop, and then after, what we're gonna do is return min dot peak. So we're using all of the functions that we use, and let's see if that works. This is peak, not peak of a hill. Boom! Implemented the heap from scratch. Okay, watch out for, yeah, keep the current index. That's how you do it. You bubble it up, bubble it down. Hope I explained everything as fast as I could. It was 40 minutes, but that's how you implement a heap. Hopefully you learned something, and I'll see you all in the next video.